Guy McPherson here again with Neil, and we're going to talk today about paleoclimates, meaning old climates, and how we determine what was going on a long time ago. So we're going to use some terminology that probably most people are not familiar with or are only barely familiar with. And we're going to talk about how we know what the climate was like until relatively recently when we were taking direct measurements. How did we figure out what the climate was like before we started with thermometers and recording those thermometers every day at a certain time of day and so on? So, Neil, you want to start us off here?
Yes, Guy. You know, this is stuff that helps me understand. And so last time we looked at the NOAA and USGS, what's called the bump handle, which is the measurement, the actual measurements at ground stations, notably Mauna Loa, and its satellite of CO2. And then that's since 1958. So we've got 75 years of that, round number, 70 years of that almost. And then we've got 800,000 years of, I'm still calling it measurement, direct measurement of atmospheric gases, because those atmospheric gases are nicely trapped in ancient ice and have been reliably measurable since the 1970s, when the methodology and technology for reliably collecting gas samples that are as small as a small bubble in a glass of champagne and measuring using scientific instrumentation what is the gas composition of that ancient air. So we can go back 800,000 years with that. And as I mentioned, and that's been going since the 70s by multiple countries. And in the last 5 years, I have found, I don't have a good graph of it, but that the ice core discoveries now go back 1.7 million years. This is just in the last 5 years, but I don't have a user-friendly data set to show or graph yet from that. I think they're still organizing that, the scientists. But the question we have is, how do you measure reliably the CO2 and other atmospheric gases and ocean minerals deposits, dissolved minerals, before 800,000 years, or before ice, if you will? What else can we use that's here on Earth that is something where you can scientifically take a measurement and estimate or analyze what was the oxygen or CO2, salinity, various other mineral aspects, and even temperature in the ancient climate? And the answer to that, I've learned, is proxies. And they are mostly based on ancient life forms and the traces they've left behind in fossils, in deposits, in strata, and the number of different chemicals and science specialties that go into this are quite numerous. So I'm just going to read out what this says here. How do scientists measure CO2 and temperature before ice cores? Guy, I'm actually having trouble reading this. Maybe you could just read this paragraph a little.
Earth's geologic history has experienced a range of natural climate shifts that provide scientists with valuable information on the overall functioning and sensitivity of our climate system to natural cycles and perturbations. But geologic climate variables are rarely recorded directly. Antarctic ice core records form a rare exception, as enclosed air bubbles allow the direct measurement of Earth's ancient atmosphere going back hundreds of thousands of years. However, current atmospheric CO2 exceeds the maximum values recorded in ice cores by more than 30%. I want you to think about that for a minute. Current atmospheric carbon dioxide exceeds the maximum values recorded in ice cores by more than 30%. That's amazing. To provide context for the future, we must look even further into the past, to times in Earth's history when atmospheric CO2 is even higher than it is today. To do so, paleoclimatologists use a variety of proxies, i.e. biological and geochemical signatures of past atmospheric CO2 that can be elicited from fossils and minerals in terrestrial and marine archives. To learn about the individual proxies used for paleo CO2 reconstructions, click on the following pictures. Each proxy description includes the templates for submitting newly published paleo CO2 estimates to the database. And we obviously won't allow you to click on those. We can't do that with the data that we have showing on the screen right now. But the point is that you can go even deeper into each one of these 8 topics or categories that you see on screen. You can dig into phytoplankton and discover a lot more than we're going to talk about. And the same holds for liverworts and boron proxies and so on.
Yeah, and in fact, I think we're going to try and include the link to this. This is very available. You have only to look or Google the search proxies, paleobiology, research, and you will probably get this in your top first page of search. I just want to go through this is only 8 that are listed here, but by my count, there are more than 20 or 30 different proxies that are used by scientists. And some of these liverworts, Guy, you were going to tell me what those are. Most people don't know. I think of liverwort as something maybe I would spread on a cracker, but I guess that's a different thing. That's liverwurst.
Yes, this is the good liver. And these are non-vascular plants. Most of us are familiar with vascular plants. That's most of the plants we see. However, some plants have different structure than, say, the daisies you have growing in your yard. And those non-vascular plants are exhibited by things like liverworts and ferns, for example. The non-vascular plants don't get very big. They can be used for paleo records, just as some vascular plants can. For example, tree rings in trees that live a long time or that do not decay very rapidly.
When I look here, I see other things that are probably from vascular plants. Am I right? Leaf gas exchange. We see those stoma that we've talked about, and then a thing called stomatal frequencies, and leaf carbon isotopes. That would be what the carbon that the leaf intakes. You can tell using am I right? Carbon dating. I learned about that in high school. That existed. I'm pretty ancient, but that existed in the 1970s when I went to middle school and high school.
Right. And then paleosols are just ancient soils. So that's another way of digging into the past, is looking at these ancient soils that hold on to some materials longer than you might expect. And you were mentioning other plant activities. Leaf gas exchange falls into the category, as does stomatal frequencies. The leaf gas exchange is just a means of determining how efficient or deficient the stomatal frequencies are, how much gas is exchanged in and out of the plant in relative to the atmosphere.
My impression, Guy, is that, as I just did a tiny bit of homework on this, that if I recall my middle school and high school biology and science class, much of this was not in the textbook. And I suspect that some of it is only, if viewers who are older than 40 or 50 have the experience in their mind that they even took an earth science class and none of this was mentioned, maybe you can tell us why.
Yeah, because some of these proxies didn't exist at that point. I think we're all familiar with carbon-13, with carbon dating, and we have only relatively recently discovered there are other ways of keeping track of historical and prehistorical information. And that includes many of these things. If you hadn't heard of paleosols or nacolite or tromas, then that's to be expected because the scientific community has made major advances when it comes to paleoclimate and paleo information in general. So looking back in time, the scientific community has become much, much better than they were even 30 or 40 years ago.
So my impression is that from just researching this, that these are numerous subspecialties. You have to become expert in the chemistry and behavior, biological sort of factors of liverwort or a certain type of leaf, and then go and you're going to out to every place you can find where there's 40 or 50 million year old strata that's accessible, and you're chipping out chunks of it and looking for leaf fossils, and then you're painstakingly, I mean, I'm not even touching the surface of the painstaking research that's required to then count, make sure you've got the right level of strata. It checks out as 50 million years old. You're focusing on that era, and then you're going all over the place looking for strata that's accessible. You're chipping it out, you're analyzing, you got graduate students working on it to come up with the data of how many stoma were in the plants that you're measuring at that time, or what was the mineral structure of the phytoplankton, what was the carbon isotope in it. Am I right? This is exceedingly painstaking scientific work in subdisciplines that no one of us, unless we were in that discipline, could follow.
Right, absolutely. The whole process of academic science is to become increasingly knowledgeable about less and less information. So you gain more and more knowledge about increasingly narrow information until in the end you know everything about nothing at all.
Well, that's true, but to my pleasant surprise, it seems like all the scientists studying this stuff have begun to collaborate and share their data, so that we get to just in the last 10 years, really, they're trying to say, well, we the people who have been doing phytoplankton measurements for the last 25 years, why don't we look and see what the leaf gas exchange people say in their data about carbon in ancient leaves versus the carbon that we're seeing in ancient phytoplankton, or the salinity or the temperature that correlates with the plant behavior that we're measuring. Let's look at the boron, the people who do nothing all day but study boron deposits in life forms, and the boron isotopes of B11 and B12, I think, or B12 and B13. Those are not vitamins; those are boron isotopes. Or the notcholite trona. That sounds like some sort of exotic herb that you would put in that today's mixologists would put in your cocktail. Would you like a Mai Tai with some notcholite trona in it? But I don't think that's what notcholite trona is.
No, those are minerals actually, and so yet another indication of the overlap and the integration among people working on these topics. I've published peer-reviewed papers having never met some of my co-authors because they were experts and they were at another university. So we exchange information, send data back and forth, and you come up with something that's useful and reasonable that no single person involved in the effort could have come up with. I come across increasingly now peer-reviewed papers that have a dozen or more authors. And I can guarantee you that some of those people have never met.
They've just been working like Trojans, carefully looking at ancient fossils through microscopes and other things to come up with data, and then see what does that data say. So let's do the reveal in the next slide. I think we're going to see a massively concentrated view of the data. So why did I include these charts for today's discussion? The chart is titled 400 million years of CO2 and temperature measurements. So I invite everyone to focus first on the top chart, which is CO2. And as last week, we did discuss, if you look at the extreme right here, and I think you can put your cursor there maybe, where it says Mauna Loa and satellites. We discussed that research, going back then into the blue line, which is all from ice cores, blue for cold ice, takes us back, and it's a logarithmic chart to about 800,000 years, right? Right there, pause there. So that's only 800,000 years, maybe to a million, by ice. So before, in the time frame before a million years, the chart becomes logarithmic, meaning as Guy moves his cursor there, it's not 100,000 years, it's a million years. Each little, bit that he moves the cursor.
Each one is 10 times greater than the previous one. So this goes from 1 to 10,000 years. This goes from 10,000 to 100,000. And this one goes from 100,000 to a million years.
And so when we look at the before, we're now looking at the realm beyond ice. We're looking at scientific evidence drawn from proxies, over 30 of them. I mean, there's so many proxies out there. We just talked about 8 of them, but there's at least 17 that are coalesced in some of the scientists who are sharing their data. I counted 17 different proxies that many scientists in each of these, not one scientist studying boron proxies. There's probably 10 or 20 worldwide. So you're not getting just one scientist's opinion or one scientific group's approach to condensing the data. And when the results are tabulated, this is multiple proxies. Let's look at what happened. You have a best fit line that looks very jagged, but it's stretched out over hundreds of millions, tens and hundreds of millions of years. And the general trend is that CO2 was much higher than the last 800,000 years of ice age, much higher. And the dots that you see that kind of are away from the line, that is data that is coming up. Some data is coming up that it was much higher in that place or much lower. You're getting the distribution, and that's how data comes in from natural sources. It doesn't all stay exactly the same. You're going to have some variations, but scientists take the predominant data and find the best fit line. And then what we see is that the data is really showing that CO2 was between, if I'm looking here, it's between 400 and 2,000 or more parts per million in the ancient Earth climate, and going down and up jaggedly. Again, it's not jagged, it's not sudden, that's over tens of millions of years. What else, can we conclude just looking at this?
Well, it's pretty obvious that it used to be a lot warmer than it is now. Yes, there's a lot of variability in those numbers, but it was much warmer than it is now. And until about a million years ago, when the temperature became cool.
Well, this is CO. The top is CO2. The bottom, let's move to the temperature one.
Right. Sorry about that.
The bottom is the temperature, and as measured by the paleobiological signatures left in life forms, we have the temperature as measured from ice core data and other data sources. And then we go back and we're into the realm of proxies. And I'm just looking from 20 feet off. There's a lot of similarity between these two graphs. And you were starting to talk about how temperature and CO2 was a lot higher way in Earth's past.
And so we see these dips correspond with ice ages, and then coming out of the last ice age, we see a relatively cool and stable climate over the last 10,000 years or so. And so that's what we're seeing over the course of the last 10,000 years is a stable, relatively cool climate up until you can't even see it on this graph, up until you have that sudden increase in global average temperature. And you can see it better up here with CO2, that the number is suddenly ratcheting up very rapidly.
Am I right that the suddenness of both the CO2 increase and the temperature increases that we're seeing is much more sudden than any of the other apparently rapid increases that we see in these charts because these are log charts? I mean, it
Yes.
just looks like a bunch of to the naked eye. It looks like everything's a jagged, sudden change here.
Yes, absolutely. It's very rapid. The Intergovernmental Panel on Climate Change concluded climate change is abrupt in its October 8th, 2018 report, Global Warming of 1.5 degrees. That's 1.5 degrees C. And here's the quote for the global warming of 1.5 degrees. Quote, these global level rates of human-driven change far exceed the rates of change driven by geophysical or biosphere forces that have altered the Earth system trajectory in the past. And they give two examples from the peer-reviewed literature. Even abrupt geophysical events do not approach current rates of human-driven change, end quote. So even the abrupt events that were identified in the past, such as these ones in the blue that you see profound increases and then decreases over time, those don't come close to what we are doing now over the course of the last few years. It doesn't even show up on this temperature graph on the lower part of this slide.
Right,
And the it does show up barely for the CO2 from the Mauna Loa satellites.
right. And the log scales are slightly different. I've lined them up at a million years, a thousand thousands. That's what that is. I've lined them up, but the log scale of the temperature chart is slightly different from the log scale of the CO2 chart, and that's just because the data. So that's why those lines look a little different.
Right.
Um, and the main thing to take from this is we have been working for the last 50 to 70 years on measurement of both CO2 and temperature on this planet, going back as long as 400 to 500 million years. And of course, there is data that goes back even further that's been collected, but the preponderance of the data is going back to 400, 500 million years. And that's what's condensed here. Finding useful charts where scientists have collected the data from multiple studies and shown it like this is a challenge. So it's always good when you can find that. To go and evaluate any of these, you'd have to go and if you wanted to take issue with it or go and look at the reliability, say, of the liverworts or the stomata, you could go and read those scientific articles and read whether they have been controversial, whether there's other scientists that are disagreeing and saying the whole method is wrong and it's really the CO2 was much lower in the past. I think those debates would have happened if that was true. What I see here is a vast number of scientists in different disciplines all doing their work, finally comparing the results of their work. And it's actually quite astonishing, the picture that emerges, that CO2 was much higher, both temperature and CO2 were much higher in our past than they have been. And that we've, by any measure, Guy, would it be fair to say that if you look at the last 800,000 years, even though we've had these things called ice ages and glaciation and deglaciation, that we've been in a stable relic compared to the past, the ancient past. The last 800,000 years has been one of a comparative narrow range of both CO2 and temperature. And then
Yes.
if you take the last 10 or 20,000 years since the last ice age, it's been even narrower and more stable. But that's until 150 years ago, right?
Yes, absolutely. And almost certainly why we're still here is because there's been a relatively slow change in the environment over the course of the last several thousand years. That's what allows civilizations to pop up and to persist, is a relatively cool, stable climate that allows for the ability to grow grains. If you don't have that cool, stable climate, you don't have the ability to grow grains. And that's absolutely necessary for every civilization so far.
Let me put some more color in what you just said, because when, as you know, I was a student of many things in college. I used college strategically to study many different things, and I'm always fascinated. I'm a polymathic learner. I've only achieved sort of below average knowledge, but in more fields than most people. So I can claim to be below average in many more fields than most people. So I'm just going to take some information that I'm fascinated by. Let's just take some civilizations, like everything we know about the ancient Egyptians, which goes back to 2000, some people even say 3000 BC, or the Mayans, which Mayan civilization collapsed without influence from contact from Europe in 1200 AD, but it was 2000 years old if you take the Olmecs and the Toltecs.
Right.
I'll just take those two, because one is in Mediterranean on one side of the planet, and the Mayan civilization is in Central America, in what is today southern Mexico, Guatemala, and Belize. The Mayans had their civilizations there, massive cities, over 300 or 400 cities that we have just found, and we're finding more beneath the canopies and dirt of the jungle. And why am I raising these? Is because these civilizations came up in the last 3,000, 4,000 years, call it. And even though this is the most stable period by any measure in our planet's past, everything I've heard about their civilization says that scientists who study their civilizations, the archaeologists, and who have looked at now such things as the grain that they were growing and the calories that were available to them, and evidence of floods and droughts and disasters and changes in the course of the Nile River. And in the case of the Mayans, the changes in their water, their droughts, their ability to grow corn, which was their key grain. They had gods. The Mayans had gods of corn, and the Egyptians had gods for the wheat and the grains that they grew. And Guy, what I would like to point out is just the variability in the last 3,000 or 4,000 years in our climate, which is the most stable period by any scientific measure in Earth's history. But it does have variability. And just the variability in the last 3,000 years has brought down, many scientists would agree, many historians and archaeologists say that one or another environmental disaster was either the cause or among the strongest causes for collapses of numerous empires and civilizations in our own human history. So when I hear variability, or on the other hand, relatively stable climate, I think of those civilizations that could not even withstand 1 or 2 or 3 years of poor grain performance from in their climate, from whatever causes, whether it was natural variability or even variability caused by the overproduction or overuse of water or other resources they may have had access to. So am I right in pointing out that variability, the stability of the last 800,000 years or even last 100,000 years has within it already shown it can bring empires down?
Yes, absolutely. And that, I lived in Belize for a few years, and it couldn't have been more clear there. You could hardly take a walk of more than a quarter of a mile without coming across some ancient artifacts, the ancient in this case being 1 to 3,000 years old, grinding stones, arrowheads, for example. So the material is still there. The hard material made from rock is still there, but the people aren't. The Mayan civilization collapsed in a very short period of time, almost certainly as a result of a profound change in atmospheric conditions, in environmental conditions that led to the inability to grow grains. And even in the relatively short time I was in Belize, people were talking about how the rainy season had gone from 8 to 9 months every year to 2 to 3 months every year. So what was going on very recently was mirroring and accelerating what had gone on in the previous few hundred years. It was remarkable.
And those civilizations, we do know now that they changed they succeeded. They were very successful civilizations in their time by our measures of success, building enduring monuments, having an elaborate social and urban structure, as well as managing relations between the rural and urban centers, all of the dynamics of cities. And again, I like the comparison because the Egyptians are a Mediterranean European civilization, and the Mayans are a completely different civilization arising. Nobody is proposing that there was deep contact between these two civilizations. There's Thor Heyerdahl, who back in the 70s and 60s and 70s wanted to show that it was possible to navigate across the continent, across the oceans. And that's an interesting experiment. But they certainly arose very separately and very differently. And yet each showed that human civilization just at their level could alter the moisture climate, the available soils and other inputs in a way that they experienced a shortage, or they experienced all it took was 2 or 3 years of poor crop production, and that caused a crisis in those civilizations.
Right. And that's the advantage of civilization, is the ability to store those grains. If you can grow a large amount of grains, you can store them and they can be kept in storage in a relatively cool, dry place for 2 or 3 years. So that's how you get through the hard times. Obviously, the storage was disrupted in ancient Egypt, in the case of the Mayans, in the case of many other civilizations. And that's what led to the downfall of these civilizations.
And it's funny, the other similarities that you had the class. I mean, all empires have this structure. All civilizations, really. You have the structure of the leaders, the monarchs, the emperors. You have the priestly class that manages the perception of gods and whether the gods are on the side of the leader, and the people are supposed to pray to those gods. And then you've got numerous classes below, and of course slaves. Both societies had slaves. Egyptian society and Mayan society, they had, then above them was small merchants and farmers, and you had specialized tradesmen. They had really all of the features of a elaborate class system. You had forms of taxation, of course. We don't know whether the oldest profession is tax collector or prostitute, or is it sewer workers? I often observe that to have cities, you need some form of waste management, and so the oldest profession is the noble profession of water and sewer, which there's evidence of in both ancient Egypt and in Mayan civilization. But let us move now to another chart, because trying to put it all together in one chart is something that scientists occasionally try and do. I'd like to go to the next chart. So this is, we're going to leave 400 million years and just look at 65 million years, a relative hot minute in climate in Earth's history here. What is this chart, and why should one care about it? It's putting all this data, again, not 400 million years, this is just 65 million years of the data, into a chart that kind of gives us a visual feel for what's happening. And so if you just put your cursor on the line, the black line at the left, you can see that it begins very hot. And the black line is where most of the data concentrates. And the shaded area above and below is the degree of uncertainty or the spread of other data points. And in some cases, there's a bigger spread because there's a more variability in the measurements that scientists get from all the proxies. Again, this is all the proxies put together. And in some places, it's very narrow. But you get a general drift that at one point, the planet was basically red hot, plus 13.6. If you look at the legend, 13.6 degrees Celsius hotter than pre-industrial, which is the P. And we'll talk about that in a minute. And as we go to the right in this chart, going further in time, we see it warms up just by the color coding. It warms up until we get to about what is, I guess, 12 million years ago, where we get to a temperature close to pre-industrial. And the ice core data here, given the log of this chart, you can see on the extreme right, it says 2.6 million. The ice core data is really the last 2 millimeters of this chart, 800,000 years. And you'll notice there's a tiny little jump up and a little yellow nub in there. And that shows, you can't even see it. It's not even, you really shouldn't even represent it on this chart, but that right now we're at 420 parts per million. That's where the yellow is approximately. 480 is up there. The climate, at 420, we're at the climate, we're at the CO2 level of well before the age of humans, well before the age of even most higher mammals. And so it's quite sudden what we're doing here at in that last part of the chart.
And we should point out that right before this chart begins, 65 million years ago, it was about 66 million years ago that an asteroid struck the Yucatan Peninsula and drove the dinosaurs and many other species to extinction. That was a mass extinction event that occurred right about where my cursor is now. And then coming out of that very hot period, it cooled off a little bit and then warmed up considerably until, in general, there's been this cooling over the course of the last 50 million years or so.
And I'm glad you mentioned that, because we haven't asked that. We should have begun maybe with this question. You know, in Earth science class, which I wish I'd paid better attention to, I think back in the 60s and 70s, they thought that first life forms began 2 or 3 billion years ago. I think it's now at 3 or 3.5. Am I right? 3.5 billion years ago is when life, what we regard as the first form of cellular life, began. Is that true?
Right. About 3.6 billion years ago, yeah.
So to put in context, we have been looking in these charts here at respectively 500 million and 65 million years of data gathered mostly from life forms, ancient life forms fossilized, or their deposits, as proxies for CO2 and temperature. I should point out there's many other things that can be gathered from proxies. Salinity, a number of other minerals, whether dissolved in ocean or in the air, can be measured in these proxies. We've just focused on CO2 and temperature, but the story of life on the Earth and the story of planetary temperature and CO2 and other gases, and the story of extinctions goes back over 2 or 3 billion years. And maybe in our next slide, if in our next session, if I can somehow find useful charts that put the data together for people in this kind of way, we will go possibly to a part 3 where we go back even further and we look at the periods, the great periods of life on this planet and geology, and we talk about those extinctions. What do you think?
And if not that, I'm sure we'll think of something interesting to talk about.
Something else. That's right. All right. Well, this is a lot of work for today. I had one final thought on this, which I want to ask the question. So some people, Guy, today, I think you're aware, there are people out there, unfortunately, in positions of political responsibility, who take this information and would say the following. Well, so don't you see? Our planet Earth has been much hotter in the past and has had much more CO2 in the past. So that means that if it goes up, CO2 and temperature goes up suddenly, it's going to be no different than the past. We're not really changing the Earth. The Earth has been this hot already, and look, we're here, and our environment will be here. And so, why should we worry? Because the planet's already withstood this kind of temperature before. And look, we're here. We evolved. We're here. They actually don't say the word evolved because some of the people I'm talking about don't believe that in evolution. But what do we make of that? Is that a legit? What should one say to the people who simply look at this data and see, aha, you've proven this? The scientists have said it was hotter by far and far more CO2. So climate change is natural and it doesn't matter.
Yes,
How do I answer that? I get that over the kitchen table. How do I answer that?
This is the argument that it's all about cycles, and things have cycled differently in the past than they do now. But look, the temperature goes up, it goes down. Carbon dioxide goes up, it goes down. So you're trying to tell me that we are responsible for this? Come on. Look at how much hotter it was 50 million years ago than it is right now. So it can't be our fault. Oh, so much nonsense, so little time. I hardly even know where to begin. The record, the ability and willingness to collect the data, to synthesize it, to organize it, to put it into a coherent package that shows very clearly that we are in the midst of the global level rates of human-driven change that are far exceeding anything that happened in the past. I mean, you just have to look at that one thing, and that's the most important thing for the continuation of species and communities and populations is a relatively stable environment. If you start messing with the environment, causing it to change in one direction or another, that spells only bad news in the past for populations and species and communities. And as a population and as a species of Homo sapiens, we should be obviously very concerned about that rapid change in environment that's currently going on.
And again, I bring up my examples of Egyptian civilization, which lasted 3,000 years, and Mayan, which lasted at least 2,000. Again, brought low by every knowledgeable expert who has looked at it believes that environmental factors caused by the Egyptian or Mayan uses of their land and their environment, in part, as well as maybe colliding with natural variability at their time, but within evil measurably changed the climate, CO2, and other factors hundreds of times faster and more than the Egyptians or the Mayans did. Is that fair to say?
Yes, absolutely. What we're doing has no precedence in planetary history, much less human history. In planetary history, think about all the organisms that came before us. At least 99.5% of the organisms that have ever existed on this planet are now extinct. And they didn't.
Yeah, and you've brought up the other thing, which is we are important, obviously, to us. That's humans' problem, is how important we are to ourselves. It's all about us. But the other species that are disappearing all around us, whose numbers are being reduced by 80 or 90% in just the last 20 or 30 years, we had already reduced those species by 80 or 90% if you look at the last 10,000 years, we had reduced higher mammals, wild higher mammals, and other large megafauna, we had reduced by a factor of 90, 80, 90, or 95 or 98%. And we've already been living with that in modern sort of human terms since cities began. But we've reduced them even further with agriculture and our spread of our own biomass, our bodies, our cities, our domesticated animals, our huge uses of land for mining, for growing the starch, the prime starch monoculture that is required for civilization. So it's not just us that is affected in what we're doing with these changes, again, which are so much greater than what the Mayans or the Egyptians did in their time. So it's a lot to take in and reflect on.
Yes, absolutely. Driving to extinction more than 200 species every day. You know, if you want the very definition of hashtag winning, look at our species. Anyway,
so we should wrap it up for today. But I can't help but think how significant it is that we've changed the climate far more than the prior major civilizations, and how much we have a lot more technology. We're able to deploy things that the Egyptians and the Mayans were not. I'll just give one example. In the wine industry in California, the water use has actually gone down per acre or per volume of wine produced, because the technology has enabled the use of sensors, a system of sensors that can measure the moisture near the root system of every single plant if you want, or certainly every 10 feet. And the sensors that used to cost $5,000 and require a $20,000 computer to measure them now cost 25 cents and require software that costs $200 and can be managed on a $1,200 laptop. So the good things are happening, but and it's managing to keep growing, just say grapes or many other products. We rely on Earth measurements to know when and where to water and grow corn and wheat and soybeans and so many other things in our agricultural system. We are relying on ever more high-tech solutions to administrate this massive agricultural agribusiness that we have. And so it looks like it's working, but how much longer can the highly techno-resilient system that we have created continue to produce if the climate goes up by just another 2 degrees Celsius on average, or heat domes form that don't just last a week, they last 3 months? I mean, when will things snap? It's a very difficult question.
If civilization's dependent upon the ability to grow grapes, I think what you're saying is we'll be fine. Unfortunately,
Indeed.
I think those grapes are an outcome of civilization. The civilization itself gave us the opportunity to play with those grapes and to ferment them and turn them into amazing products.
Yeah.
I think
we just have to hope.
I think we should stop at that note right there.
All right, sir.
Anytime you end with wine, I think that's a good thing.
I think I need something stronger than a glass of wine. I think some scotch on the rocks would be good. It's only midday, but somewhere the Irish are drinking already. So
yes. All right. Thank you, Neil. Stay tuned, everybody. We're going to do this again in another week.